Hello everyone, my name is Jay Lim and I'm a PhD student in Rutgers University advised by Santosh Nagarkate. It looks like nowadays everybody's creating their own representations for approximating real numbers. I'm not saying that it's a bad thing, but it means that we should have a math library for each of these new representations. So today I'm going to talk about our experiences in trying to create a math library for these representations. In the last few years, we saw a number of new representations for approximating real numbers being proposed. John Gustafson proposed a posit representation which provides tapered accuracy as you have seen from Sangeeta's talk. Google and Intel proposed bfloat16, which is a 16-bit floating point representation with 8 bits for exponent. And just a couple of months ago, NVIDIA proposed TensorFloat32, which is a 19-bit floating point representation with 8 bits for exponent. These representations are proposed for the applications in neural network and HPC, and as such, these communities are very excited about these new representations. However, because these representations are so new, there are no math libraries designed specifically for these representations. Because they're primarily used in numerical applications, it would be really great to have native math libraries for these representations. Now, one important requirement of a math library is that it should produce the correct value for all inputs. If the math library itself produces incorrect results, then any application using this math library will produce incorrect results, even if the rest of the application is numerically correct. So in this presentation, I would like to share with you the experiences we had with creating a correctly rounded math library for these new representations, the challenges in creating correctly rounded math libraries, and our solution to tackle this problem. So let me start off by first talking about what is correctly rounded math library. To illustrate, here's a number line in real numbers, and here are some consecutive bfloat16 values on the number line, and bfloat16 representation can only represent finitely many rational values. So you can't exactly represent irrational values like log 10 of 1.8, and you have to round them to a bfloat16 value according to the rounding rule. In this talk, we will use the round to the nearest, pi goes to even rule, so log 10 of 1.8 gets rounded to b1. So if the log10 function in our bfloat math library produces b1 for log10 of 1.8, we say that it produces the correctly rounded value, and if it produces the correctly rounded values for all inputs, then we say that the math library is a correctly rounded math library. But in the past, creating a correctly rounded math library has always been a difficult task, and let me show you why. In a high-level perspective, the most widely used method to create math library function for any transcendental function f of x is to first mathematically derive a polynomial approximation of f of x. This polynomial can be derived using minimax approximation techniques like Remez algorithm or Chebyshev polynomial approximations, but because p of x is an approximation, it will have an error compared to f of x. But this error can mathematically be bounded so that we can tell how much error we can expect. Once we derive p of x, the next step is to implement p of x using a higher precision representation than the target representation for the math library. For example, in our case, we're trying to create a bfloat16 math library, so we could implement a of x with doubles. And since a of x implements p of x using double, we're bound to have some error compared to p of x. Finally, we round the output of a of x to our target representation, bfloat16, but because of the error of p of x and a of x, we get the wrong result. So how small should be the window of error for p of x and a of x? To explain this, observe that given the value b1, which is our correctly rounded value, there is an interval, this gray interval around b1, where all values in this interval gets rounded to b1. Our log 10 of 1.8 value is also within this interval, and this is why log 10 of 1.8 gets rounded to b1. So for p of x and a of x, which approximates f of x, to produce b1 when rounded, the result of a of x has to be within this much of error from f of x, especially if the value of f of x is so close to the boundary of the gray interval. Otherwise, even the tiniest over-approximation to the right will result in a wrong result. And you can reason that if the f of x value is even closer to the boundary of the gray interval, the margin of error may be infinitesimally small. So are we doomed? Well, actually, let's take a quick moment here and think about what a correctly rounded math library means again. Our math library is a correctly rounded math library if it returns b1 when we ask for log 10 of 1.8. The goal of our math library is not to approximate log 10 of 1.8 as closely as we possibly can. Instead, the goal of our math library is to return b1 if the input is 1.8. Then what should be the goal of a of x? The goal of a of x should be to return a value within this gray interval we talked about, so that if we round the result, it rounds to b1. In other words, our a of x can return this value, this value, this value, or this value, and still the result will be correctly rounded to b1. And now our margin of error for a of x is significantly larger than what we had before. And this is the intuition in our approach, which was inspired from the minefield technique by John Gustafson. Our insight is that we should derive a polynomial approximation and its implementation a of x such that the result of a of x produces a value within this interval. Then the rounded result will be the correctly rounded value. So to this end, our approach in high level has two steps. First, we identify these gray intervals for the output of f of x for each input. This step is inspired by the minefield technique, but the minefield technique has to manually come up with the polynomial approximation. So instead, we generate p of x by using these intervals as linear constraints, and we use linear programming solvers to create p of x. So now let me explain our techniques a little bit more in detail using examples. First, given a function f of x that we want to approximate, we identify all input values in our representation and compute the correctly rounded result. For each of the correctly rounded result, we identify the interval such that all values in the interval rounds to the correctly rounded result. These intervals are basically a constraint for our polynomial p of x. In other words, our goal now is to fit a polynomial that crosses all of these intervals. So how do we create such a polynomial? We'll observe that these intervals basically define linear constraints on p of x. The output of p of x should be within these values for each of the inputs. Because they are linear constraints, we can create a linear programming problem in terms of trying to identify a set of coefficients of a polynomial that satisfies all the linear constraints. If we can find a set of coefficients, then we can generate a polynomial that produces the correctly rounded result for all inputs. So we can give this problem to an LP solver and solve for the coefficients. Now, if you have looked at math libraries, you will know that there's a lot more to a math library, like range reduction and input transformation and so on, and we have techniques to deal with them as well. If you would like to learn more about our techniques in dealing with range reduction, please feel free to email me and I will be happy to answer any questions. Going back to our technique to produce correctly rounded math libraries, we were able to use our technique and create approximation functions for a number of transcendental functions for bfloat16 already. Internally, the library uses double computation, and for all of these approximation functions, our math library produces the correctly rounded value for all inputs. During the evaluation, we also wanted to know what would happen if we approximate these functions by using the float math library. So we did an experiment where we convert the bfloat16 input into float, use float's math library to compute the result, and then round the result back to bfloat16. But what we found out was that there was a case where this produced a wrong result. This case is especially interesting because the float math library produces the correctly rounded result for float, but when we round this result to bfloat16, it became a wrong answer. So hopefully this result convinces you that it is important to create a native math library for each representation. Additionally, we were able to create correctly rounded approximation functions of a number of transcendental functions for 16-bit posit representation, and also we were able to create an approximation function of log 2 of x for a small input domain for the float representation. We are still actively creating correctly rounded approximation functions for other transcendental functions as well, so this list will grow larger. In conclusion, many exciting new representations for approximating real numbers have been proposed recently, and there is excitement in the neural network and HPC community to use these representations. However, these representations do not have native math libraries yet. So we present an initial effort to create a native math library for these representations that produce correctly rounded results for all inputs. Our technique generates a polynomial approximation of transcendental functions by approximating the correctly rounded result rather than the actual f of x values, and we were able to use this technique to create a number of correctly rounded approximation functions for various representations, such as bfloat16, 16-bit posit, and float. Thank you very much, and if you have any questions or comments, please do not hesitate to email us.